Scientists have discovered a massive 12 to 16 kilometre wide asteroid impact crater in Western Australia. The findings, reported in the journal Meteoritics and Planetary Science, is one of two newly discovered impact structures unearthed by the same team, with the other located in Central America. The Australian discovery was made at Yallali, just north of Gingin. Researchers from Curtin University identified the buried crater after investigating surface rocks called breccia. Scientists were able to identify telltale microscopic evidence of shocked quartz from the breccia, formed as a direct result of an asteroid impact. The authors believe the impact happened during the Cretaceous era, about 85 million years ago. The second crater was discovered in thick jungle in the Central American nation of Nicaragua. One of the study's authors, Dr. Aaron Cavosi from Curtin's School of Earth and Planetary Sciences, says his team received a sample of black impact glass about the size of a marble. When they examined it, they discovered the sample contained shocked zircon, features only found in structures formed by impact. The authors used argon dating to determine the impact occurred about 80,000 years ago. Cavosi says it was amazing to find solid evidence of a meteorite impact in such a tiny sample.
The Yallali impact crater in Western Australia, the new one we just discovered, is about 100 k's north of a town called Gingin, which itself is north of Perth. So if you're in Perth, it's only a 2 or 3 hour drive to get up there. It's pretty easy to find.
And of course, Gingin's the location of the Gravitational Observatory.
There's a lot going on in that area.
Indeed. What made people look for this particular crater in the first place?
Well, this one was a tough nut to crack. They say in science that you stand on the shoulders of giants, and
Indeed.
This is a case like that. There were reports from about 20 years ago where some researchers at University of Western Australia and the WA Museum had described a possibility of a buried impact crater in this area, and that means that nothing of the crater itself is exposed. What they found was a little bit of a funny rock called breccia. We can talk more about that later. And they made some preliminary studies on it. There was also an oil company that drilled the feature and found some unusually disturbed rocks where they shouldn't have been. And so there was an indication that something was going on here. But at the time, they didn't have enough evidence to confirm what it was.
And the opportunity arose to go there and take a better look. And what'd you find?
Well, we came into this with new eyes. One of the things that we do at the Space Science and Technology Center at Curtin is we study the kind of evidence, the kind of damage that happens to rocks and minerals that's unique to the impact process. It's really quite startling how much damage at all scales, from kilometer scale down to a millimeter or even smaller scale, an impact does. An impact creates such strong pressures and forces that some cases the atoms of minerals can get rearranged and form other minerals in that process. But what's more common is that there's microscopic damage that's only caused by these very high pressures. So we went out to look to see if we could find evidence of that microscopic damage.
And what'd you find?
Well, the only thing, as I mentioned, that one can study on the surface is this funny rock called breccia. Now, breccia, for lack of a better phrase, if you took a whole 5 or 6 normal-looking rocks and put them in a blender and poured it out and baked it, that's pretty much what a breccia looks like. A breccia has a lot of different pieces of other rock. In an impact setting, breccias form because when this impactor comes in, it literally partially melts and mixes and stirs up a lot of rocks. Some of them get thrown out of the crater and then they just land. And where they land, it's like you just poured something out on the ground and there it is. It turns into a rock over time. So we found small amounts of this breccia exposed simply because it had been thrown out of the crater by about 5 kilometers. And we studied that, and we found the common mineral quartz. And when we looked very carefully at that quartz, we found the evidence of shock deformation, these microscopic features that are a telltale sign of impact processes. This project was led by an undergraduate student, an honor student named Morgan Cox, and she did the hard work to find those quartz grains.
The rocks being studied were primarily ejecta. What does that tell you about the crater itself? What can you learn about the likely size of the impact crater from looking at the ejecta that's been thrown from it?
Ejecta is a wonderful material, and it's also wonderfully complicated. Again, when an impact happens, it pushes the crust of Earth down under great pressures, and when the crust rebounds back up, it often spits out a lot of rock and melt and vapor, and it can land in the vicinity or far away. In this case, the ejecta contains a lot of the material that tells us about what those rocks were in the subsurface. The problem with this site is that it's buried and covered by several hundred meters of much younger sediments and rocks. So in a way, unless you drill it or have some other means, you can't really tell what rocks are down there. It's in an area called the Perth Basin. And the Perth Basin has been explored for water and other things. And so people know a little bit about the geology of the Perth Basin, and we know what kinds of rocks we should expect to find down there. And in this case, because the crust had rebounded, rocks that normally are much deeper were much closer to the surface in drill core. So that was the first bit of evidence that something funny was going on. But when we examined the breccia, we could look at all of the different rock fragments, and we could tell, okay, we see a little bit of this sandstone, a little bit of this mudstone, a little bit of this siltstone, and different kinds of rocks. And that also tells us what rocks were involved in the impact. This gets a little bit towards the age of the event, which is a tricky thing to try to peg. We pegged the age at about 85 million years, plus or minus a few million, by looking at what rocks were involved in the impact. So we knew if we see this particular unit involved in the breccia, that unit had to be there in order to be hit and incorporated into the breccia. And so it provides a little bit of evidence on, okay, here's some regional rock units that we recognize as little bits and clasts and shards in this breccia. If it's in the breccia, it must have been deposited already at the time of the impact. And so it helps us narrow down the age. The best number we can assign to the age is about 85 million years, plus or minus a little bit. And so it puts it in a cool time period called the Cretaceous. Lots of dinosaurs walking around. It's before all the dinosaurs got knocked out by a much bigger impact in Mexico. It's 65 million years ago. So they still had 20 million years of a good life ahead of them at the time of this impact in WA.
Were you able to work out the size of the crater at all? Have you done enough core drilling to work out how big the impact crater would have been?
Well, there were initially only 1 or 2 cores taken. And so they made an estimate based on cores and a little bit of seismic data. Again, the company was exploring this for petroleum potential, and they came up with a value of around 12 kilometers in diameter initially. That's what they thought. Based on our data, once we confirmed with Shocked Minerals that it truly was an impact, we ran some numerical models. One of our members here at Curtin, Katerina Milkovich, ran numerical models that suggested it could be up to 16 kilometers in diameter, which is a pretty gosh darn big hole in the ground if it were to happen today. It would be a city buster, no doubt about it.
Does this tell you anything about the progenitor that created it?
Well, based on modeling, we can kind of tell its size. It's probably, a few hundred meters, but it's a little difficult to tell what kind of rock from space made the Galilee impact, and that's a little trickier to get because you'd like to get either pieces of that meteorite or maybe some melt that might contain a little bit of melted meteorite in it. So it's a little hard to tell what kind of rock it was that hit it.
Where to next?
Well, in terms of Galilee, it's kind of great because finding new impact structures in Australia just adds to the geological heritage like mad. Prior to this discovery, there were 27 confirmed impact structures. This brings it up to 28. There undoubtedly are more impact craters in Australia all across that are waiting to be discovered.
Including some of the biggest impact sites known on the planet. There's this huge one stretching from the far west of New South Wales well into South Australia.
Yeah, there is a proposal from 2015. There may be what could be the largest impact structure in Australia.
And of course, this discovery in Western Australia wasn't the only one that your team was involved with. There was another discovery, also published in the journal, in Nicaragua. Tell me about that.
Well, yeah, we got pretty lucky on this one. Our results, we have lots of projects that run ongoing all the time, and we slowly do our detective work very carefully and methodically, and we don't release results until we're very confident of them. In this case, at about the same time we released the results for the Galilee impact crater in Western Australia, we also confirmed a new impact structure in Nicaragua in Central America. This one is called Phantasma, and interestingly enough, it's a similar size structure to the Galilee. It's about 14 kilometers in diameter. This one's not buried, but it has a complication that it's covered in jungle, and so there's not a lot of good exposure. There's a little bit. But the major difference is it's much younger. It's been dated. We dated it here at Curtin. There was some glass that had been recovered from the site. Impact glass has a very lovely quality to it in that it's produced during the impact event, and then it's immediately quenched, and so meaning frozen. And so we can do argon isotope dating to determine when that glass formed.